this next few modules, we're going to continue from where we left off last time, where we did introduce the technique, some basic techniques of Monte Carlo simulations, and then consider somewhat more advanced approach to Monte Carlo, you can say. But I mean, first of all, we'll deal with the notion of random walks and do some theoretical analysis with them, and then extract the main key results of random walks, which pretty much everybody should know, I guess, and try to make contact with this using some simulations, right, using Mathematica. So today, in this module, the agenda is to just introduce this random walk model in 1D, and then build up the model so that it can be put on a computer next. All right. Okay, so think of a person who is on the origin. Let's say he's a drunkard who doesn't have a sense of purpose in life. So with probability P, he chooses to go to the right. So let's say he's confined to live on the x-axis, right? I mean, of course, you can generalize this to higher dimensions. Suppose he's confined to walk along the x-axis, but at every unit of time, so he doesn't keep on moving, it's not continuous motion in time or space. We'll consider the discrete problem first. So he can be either at the origin, or he can be at +1, +2, +3, so on, right, in some units, doesn't matter what. And time also moves forward in units of one unit, which could be whatever, 1 second or a minute or whatever you want to choose. And after every unit time, so our friend makes a choice whether to go right or go left. And so let's say after capital N number of steps, so we want to ask how far what is a typical distance which our friend would manage to cover if he is given n steps, right? So this is the type of question. So it's a stochastic random variable. It's not going to be, there is no definite answer for exactly where he's located. Is not something that you can calculate, because there is even he doesn't know where he will be exactly precisely after n steps. But it turns out that you still know a surprising amount of information, in terms of the average location or average distance from the origin and so on. You can ask a lot of questions, and there are very precise answers to some of these questions one can formulate in a stochastic way. So that's the beauty of stochastic methods already comes out in something very simple like the random walk problem. So let's say that n1 steps are taken to the right and n2 steps are taken to the left, right? So clearly capital N must be equal to small n1 plus small n2, because if n1 is, there is no option of not taking a step, right? That's the simplest model we are considering. You can also make this model a little more complicated and say that with some probability, some other probability which is such that P plus Q plus this new probability that we are introducing is equal to 1. The person stays at a location, right? You can say that with probability P he moves to the right, and with probability Q he moves to the left, and probability Q tilde, let's say, he stays where he is. So that P plus Q tilde is equal to 1. So that option we are not considering here. We are saying that P plus Q equal to 1, and so the person either moves to the right or to the left at every time instant when a decision needs to be made. So therefore capital N is equal to n1 plus n2. So a quantity of interest for us is small m, which is just simply defined as n1 minus n2. So you are interested in what is the typical distance that our friend manages to cover as a function of time, right? It could be a negative number, but you will see in some time that actually we care about the modulus of m, or even more convenient is actually m squared. So you are interested in finding out what is the typical distance squared of distance covered by this person as a function of capital N. If you take capital N m number of steps, what is the typical m, right? It's a In fact, it will turn out that you can compute the full distribution itself, the probability distribution involved. Okay, so let us say that there is no memory, right, in the motion of the random walker. So at every instant of time, the person basically doesn't care about what they did in the previous step, right? So you can think of it as tossing a coin every time. He goes to a step, then before he makes up his mind next time, he just tosses a coin, and with probability P, the toss is going to give him heads, and which he'll go to the right, and with probability Q, he's going to get tails, and he's going to move to the left, right? So these kinds of this type of a model can well be applied to the motion of stock prices, for example, right? But there it turns out that this kind of a memoryless model perhaps is not the most accurate, although some people have argued. So there are mathematical models of stock prices where people argue that it's basically a completely random walk, right? And there are anecdotes where there was group of academicians who just cooked up data using random walk and then random walks, and then they just showed this data to some financial analyst, and they predicted, oh, we see a pattern here, and then you should put your money in here and it's going to go up or whatever, right? So, and basically their argument was that their data generated from random walks were completely indistinguishable from realistic data, where people claim that there is some hidden order there, right, which is predictable, right? Predictability is what is of great interest in the context of stock prices. But it turns out that in fact there are other academic discussions where people have argued that in fact it is not really a random walk, there is some predictability involved, and in fact that has to do with the fact that there is often some memory in the motion of stock prices or whatever. At every instant it's not going to be completely cut off from what happened in the prior instant. So typically there is going to be some speed associated with it, and it keeps going in a certain direction, and then of course there is a randomness associated with it as well. And there if sufficient people start seeing a trend, then they try to exploit it, and therefore the trend gets reversed there. So in some sense the whole system enforces a certain amount of randomness is an essential aspect of that system. But okay, so that's just a small digression into how a model of this kind can be applied in the context of stock markets. But for our model we're very, very simple. So we don't have any memory effects here. At every instant it's a fresh coin which is tossed. With probability P you go to the right, and with probability Q you go to the left. So the number of ways in which capital N steps can be composed of small n1 right steps and small n2 left steps is simply n choose n1, right? Now for each of these possibilities, the probability is given by P times P times P times P so on n1 times, and Q times Q times Q so on n2 times, right? So you have to tag along all these various possibilities, you have to count them, which we already did, n choose n1 times P1 to the power n1 times Q to the n2. So therefore in fact that's all there is to it. Therefore the overall probability of finding the random walker at position M after n steps is simply given by n choose n1 times P to the n1 times Q to the n2, right? So this is already a bit of a result. So now we can invert this n1 and n2 and write n1 as capital N plus m by 2 and n2 as capital N minus m by 2. All I have done is just to solve for n1 and n2 in equation 1, straightforward, and then we can write the final solution in a more convenient form, right? So ultimately you are interested in probability of being at position M, given that you have taken n steps, is given by this expression n factorial divided by n plus m by 2 the whole factorial times n minus m by 2 the whole factorial times these two factors. So of course here notice that if n is even, then m is also going to be even, right? So you cannot have m odd, right? So this is um, um, so for example, so let's just think of the case where you just walk once, you take one step. If you take one step, then for sure you could have gone either to the right or to the left. So there is no question of the walker being at 0, right? So so you can ask whether they're at 1 or whether they're at 3. So after 2 steps, then for sure you're guaranteed that your walker is going to be at an even position. There's no possibility of them being at the odd position. And the third step, they're guaranteed to be at either 1 or -1 or +3 or -3. All these possibilities arise, but for sure they cannot be at the origin, they cannot be at 2 or 4 or whatever, right? So this is ingrained into this equation, right? So okay, so here's a homework question for you. How can you be sure that this is a reasonable probability here, right? So can you check this? Is it already normalized, or is there some more work one has to do to normalize it? So I'm claiming that it's already normalized because I have used a nice argument involving probabilities to get to another probability, and I believe that I have done my counting correctly. But you should check this, and the way to check this is to just sum over all possibilities here, right? So probability is a quantity which must add up to 1 if you sum over the entire sample space. In this case, so m can only go from the maximum value of small m is of course capital N, right? So if all steps are taken to the right, then n1 minus n2 is exactly equal to m, because n2 is 0, right? Now on the other hand, if so the smallest value of n in magnitude is 0, but it can also be minus n. If all steps were taken to the left, it could be minus n. So what you should do is just sum over all possibilities of m. First start small, take capital N to be 2 and 3 and 4 and so on, and then play with it for yourself, and then you see a pattern why they should just sum up to 1, and then you will see that there is a simple direct way to solve for this. That's homework for you. Okay, let's move on. So what I want to do is show you some tricks here. Some of you might have seen this, but it's very clever, the way to compute the mean and variance of this distribution. So we have the condition p plus q equal to 1, right? I have said it, but it was also sort of implicitly clear that there is no possibility of the random walker at any instant of time to not make a choice. He either goes to the right or to the left, therefore p plus q is given to be 1, right? Now consider this quantity z, right? I mean, you'll see in a moment why I am doing this at all. So I have z is equal to p plus q the whole power n. For now, you think of this as just some two variables p and q. You're not already putting p plus q equal to 1. We will do that later on. So it's just some trickery involved here, right? So I expand p plus q to the whole power n and write it as this series summation over n1 going from 0 to n choose n1, which is n factorial by n1 factorial times n minus n1 the whole factorial, p to the n1 times q to the capital N minus n1. So this, let me call this as equal to Pn of n1, because you see this is exactly the expression I have for my Pn of m or n1 is the same. So if you are paying attention, this already gives you a proof of why this probability is normalized. You see that? So if you see that, don't see that, spend a minute, you can pause the video here and go back to this homework problem and then connect to this expression for z I have, and then quickly check that indeed it's a normalized probability distribution probability. Okay, so the mean number of steps taken to the right is just given by summation over n1, and you have to do n1 times Pn of n1, which you can see that now you see the power of this expanding this type of a quantity called z. See, think of this z as simply an algebraic expression. For a moment you are not supposed to you are not supposed to put in p plus q equal to 1. Don't think of it as I am taking a derivative of 1 with respect to, just think of it as a derivative of some function of two variables p and q, and then you just do dou z by dou p. Then you see that you will get n1 times p to the n minus 1. So, this n1 here is, it appears in the sum when you do this dou z by dou p, and then but you are losing a power of p. So, you have to multiply by p so that you adjust appropriately for all the powers, and then you see you can evaluate this expression. So, what I would suggest is just do dou z by dou p and then multiply it by p, and then check for yourself that indeed that is equal to this sum over n1 equal to 0 to n1 times Pn of n1, and then you can of course very quickly evaluate it. Now that you have this, you can evaluate it, and then you see that the number of the mean number of steps taken to the right is simply given by average of n1 is equal to capital N times p, right, because dou z by dou p is going to be just n. Yeah, you see that. So, it's just, you can, if you take a derivative, it's n times p plus q the whole power n minus 1, and p plus q, now you put in p plus q equal to 1. So, you will just remain with n for dou z by dou p, then it's just n times p. It's some clever trickery. Surely there are other ways of doing this as well, but this is one nice way of doing it. Okay, you can go ahead and actually find the second moment as well. It's of great importance here, is to find the average of n1 squared. So, here you just simply take a derivative of with respect to p once again of dou z by dou p. So, in other words, you are looking at dou squared z by dou p squared, the second derivative, partial derivative, and so now you see that you have n1 times n1 minus 1, right. So, actually you are interested in n1 squared now, but we will see that using n1 information and some trickery of this on the left hand side, we can actually evaluate this as well. So, you should check this. What does it involve? Simply taking a derivative and over this sum and writing it explicitly like this, and then you multiply by p squared. Now, when you multiply by p squared, you are going to get p to the n1. You have compensated appropriately for the loss in the power of p, and then you have to collect these terms. On the one hand you have n1 squared, but you have minus n1. So, you should verify this and check that indeed you have n1 squared times the probability n of n1 minus n1 times Pn of n1, right. And in fact, this quantity p squared dou squared z by dou p squared is actually nothing but the variance of this random variable n1, right. N1 is the number of steps taken to the right. Okay. So, this in turn yields, after putting p plus q equal to 1, all you have to do is take this derivative n times p plus q the whole to the n minus 1, right, and then again take another derivative. You will get n times n minus 1 times p plus q to the whole n minus 2, and then you put p plus q equal to 1, right. You should reserve this stuff of putting p plus q equal to 1 to the last, right. This is some trickery. Ponder over this, and then you will see why it makes sense, right. Then you see, once you have this, you just plug in here n times n minus 1 p squared. So there is a second p also which comes in here, right, which comes in because you have p squared here, p squared sitting here. So, you have n into n minus 1 times p squared is equal to average of n1 squared minus, which is unknown, minus n times p, because we already evaluated this, and therefore, you see that average of n1 squared is actually now known. It's going to be just n into n minus 1 times p squared plus n times p. So, once we have this expression, we will go back and we will find out what is first of all, let us find the variance. Sigma squared is equal to average of n1 squared minus average of n1 the whole squared, right. So, check that this indeed makes sense. So, finally, the expression is just n times n minus 1 times p squared plus n times p minus n squared p squared, which after some manipulation can be shown to be just simply n times p times q. Okay. So this is for you to check this. All you have to do is use the fact that p plus q equal to 1, and then you can show this. So this is homework to go from equation 15 to equation 16 using p plus q equal to 1. Okay, so we have obtained an expression for the mean of n1, we have obtained an expression for the mean of the square of n1, right? And therefore using that we have found the variance in n1. Now actually we are interested in the mean and variance of the random variable m, which is the typical distance, which is a measure of the typical distance you are from the origin. So it is actually n1 minus n2. You can go ahead and compute this in terms of n2, and then you put in the variable m as n1 minus n2, and that is one way of doing it. So another way is to do the following, right? You just solve for m in terms of n1. So since n it's already given here, so now from which we have m is equal to actually 2, you eliminate n2, because n2 we have not really found out the information about its mean and variance. So you just compute small m is equal to 2n1 minus n. Now the average of m is simply 2 times the average of n1 minus capital N, and the average of n1 we already found is n times p. By the way, the fact that the average of n1 is n times p is also very reasonable physically, right? So basically what are you saying? You're saying that if you take one step to the right, the probability of going to the right is p. So the probability that after capital N steps, the probability that you have taken what is the average number of steps you have taken to the right is just going to be capital N times p, right? Because in another way of thinking of that is it's a bit like your Monte Carlo in some sense, right? So the average the probability, if suppose you did not know what p is, how would you find out? If you had a machine which would generate a random walk for you, you just simply count. After the first step, you'll find out whether they went to the right or not, and then you get data for n steps, and you ask yourself how many of these were to the right. So you will find a certain number which actually is n1, and then so you will just divide n1 by capital N and say that should be the probability of going to the right, right? So that's in the spirit of a Monte Carlo. Like, this is how we found out what is like how many points fall inside a region, right? If you want to compute the area of a certain region, for example, with respect to the total number of darts thrown and so on, right? And so in fact, if you want to find out whether how biased a coin is, this would be the method, right? You would just toss it, and then you find that it has do you get heads or tails, then you find out again, then you keep on counting. So if you take a very large number of trials of this, and you are finding that actually 65 out of 100 are heads, so then you say that it's a biased coin. It's not 0.5 and 0.5, but actually it's 0.65. So that's going on here. So now we have, once you have n1, average of n1, you can also quickly find the average of m, so which is simply given by 2 times n times p minus a half. So the variance is a little more involved, the computation of variance, but not necessarily out of reach. All you have to do is expand this. So then you have 2n1 minus n the whole squared minus 2n1 minus n average of this the whole squared. Then you carefully pull out these factors, right? So then you have 4 times 4 can come out of the average, doesn't matter. So n1 squared minus 4n times average of n1 plus n squared minus 4 times n1 average whole squared minus 4n times n1 average plus n squared. If you collect all these terms carefully, so you will find that in fact the variance of m is related to the variance of n1, and it's just a matter of a factor of 4. So just 4 times the variance in n1 is the variance of m. So you can immediately write down the answer, which is the variance in m is actually simply 4 times n times p times q, and its mean is 2 times n times p minus a half. So one immediate thing you would observe is, of course, what happens when p equal to half for the unbiased coin tosser or random walker. So basically somebody who treats both directions, equally carefully or equally carelessly. They don't care where they're going. So with probability half if he's going to the right, and with probability half he goes to the left, then on average you expect that after capital N number of steps he has basically moved not at all. He will be very close to the origin. So the mean is indeed at the origin. There is no drift. But the spread is, it turns out, is actually the more interesting quantity when you consider this. So although the mean of this random variable is 0, their variance will turn out to be n. So in fact, so that's typically how far away he is going to be from the origin. He is not going to be sitting on the origin like the mean seems to suggest. So in fact, it's the variance that counts. So you have to take the square root of this, and so he's actually going to be very likely close to a distance of square root n away. It could be on the right side or to the left, that cannot be ascertained, but he's not going to be on the origin. So this is actually an example of how the mean of a distribution is not necessarily always the most meaningful quantity. Sometimes it is actually the variance or the root of the variance, which is the standard deviation, which carries more useful information than the mean. And so this is one such context where actually the typical distance of your random walker after n steps is actually square root n, right? So let's look at this. This is a special case. I have already talked about this, but let's do it more formally now. So if I to put p equal to q equal to half, so indeed average of m equal to 0, average of m squared minus average of m the whole squared, average of m square, with the bracket on squared, the this angular brackets squared. So this is equal to n, and so equivalently this is a very, very important result. Ultimately, with all this simple set of arguments which seem very logical, we have managed to show a very, very important result which appears in all kinds of contexts whenever there is a stochastic motion involved, and that result is just average of m squared is equal to n. So if you take capital N steps, in fact basically you are moving only square root of n if you are a random walker, right? So if you have no purpose in life and if you are just simply exploring every direction, so you can imagine that although you take n steps, you would only go square root of n. And the best you can do is of course to go n, right? So if it's of order n, it means that you are more or less going, all your steps, every step that you take does count for your overall motion. So, and that's what is called a ballistic motion, and this is called a diffusive motion for a reason which we will show in a moment. So this is connected to the diffusion equation and so on. Okay, so the main result from this discussion is average of m squared is equal to n, and in fact you can do better and get a distribution Pn of m is equal to this binomial distribution, which using Stirling's approximation, which is going to be homework for you to show, is actually the Gaussian distribution. It is a sharply peaked distribution. The more steps you take, the more sharply peaked you are around your origin, and the spread is going to become smaller and smaller. You will see this, right? So the Stirling approximation is also listed here. So log of n factorial is equal to is given by this complicated looking expression, but it's actually a very nice tool. All you have to do is just plug this in and take care of all the simplifications, and then you can show that it's a Gaussian distribution. All right, thank you.